Now let's have a look at how the competition to identify the best columns for expansion is carried out by the hippocampus. This illustrates the major neuron types and connectivity paths within CA3 and the dentate gyrus. In the dentate gyrus, there are excitatory granule cells, and there's also excitatory mossy cells, and there's reciprocal connectivity between them. And of course, this reciprocal connectivity is excitatory in both directions. In CA3, there are pyramidal neurons very similar to those in the cortex. Both the CA3 pyramidals and the granule cells in the dentate gyrus get inputs from the same source in the entorhinal cortex, layer 2 actually. So some neurons in the two structures could have relatively similar receptive fields. CA3 pyramidals output to CA1 pyramidals, and CA1 outputs drive cortical receptive field expansions. Within CA3, there's massive feedback from each pyramidal neuron to many other pyramidal neurons within CA3. One CA3 pyramidal actually gets several times more inputs from other CA3s than it gets from the entorhinal cortex, for example. And the CA3 pyramidals also target mossy cells in the dentate gyrus. There's also connectivity the other way, from the dentate gyrus to CA3. But this connectivity is both excitatory and inhibitory. Granule cells excite CA3 pyramidals, but they also inhibit pyramidals via interneurons in CA3. So what's the function performed by all this connectivity? Well, as I've said, there's a positive feedback loop within the dentate gyrus, with granule cells exciting mossy cells and mossy cells exciting granule cells. There's also a positive feedback loop within CA3, with each CA3 pyramidal exciting many other CA3 pyramidals. And there's a positive feedback loop between the positive feedback loops, with CA3 pyramidals exciting mossy cells and granule cells exciting the pyramidals. And there's one inhibitory path from granule cells back to the CA3 pyramidals through the interneurons. The ratio of excitatory to inhibitory action actually varies with the degree of granule cell activity. If granule cell activity is low, the excitatory activity is a bit stronger than the inhibitory. But as granule cell activity increases, the inhibitory begins to swamp the excitatory. So overall, you've got two positive feedback loops in CA3 and dentate gyrus, linked by a positive feedback loop, and an inhibitory link to damp things down. So, what's all this connectivity achieving? Well, because granule cells and CA3 pyramidals get inputs from the same source, a receptive field in the dentate gyrus could be quite similar to some receptive fields in CA3. And the granule cells tend to target CA3 pyramidals with similar receptive fields over both the excitatory and the inhibitory routes. So how does this connectivity manage selection of targets for receptive field expansion? Well, if the current cortical experience is familiar, in other words, there's no novelty, then there'll be strong input into the entorhinal cortex from all areas of the cortex. That'll mean there'll be strong activity in all the granule cells. So the inhibitory path into CA3 will predominate, which will shut down CA3. CA3 will produce no output to CA1, and there's no receptive field expansion. But now suppose there's some novelty in the current cortical inputs. Some entorhinal inputs to the hippocampus will be a bit lower. The granule cells, with receptive fields corresponding with those lower activity cortical regions, will therefore have lower activity, which will allow build-up of activity in CA3 neurons with similar receptive fields. In other words, the receptive fields in CA3 that correspond with low activity cortical regions. The feedback within CA3 will establish activity in a group of pyramidals with the best fit to the cortical regions of lower activity. As the CA3 activity builds, the feedback to the mossy cells increases, increasing granule cell activity, and the increasing inhibition of CA3 will limit the build-up of the CA3 pyramidals. So overall, the degree of activity in CA3 will be proportional to the degree of novelty in the current cortical experience, as indicated by lower receptive field detection in some cortical regions. And the active receptive field detections in CA3 will correspond with the groups of columns in the regions of lower cortical activity that are most appropriate for receptive field expansion. This CA3 activity is then released to the CA1 pyramidals with similar receptive fields, and from CA1 on back to the cortex to drive receptive field expansions. Each time cortical receptive field expansions occur, there will be a need to update the hippocampal receptive fields to include information about the current simultaneous expansions. And this raises the question of how the receptive field changes in the hippocampus itself can be guided. Remember, from our earlier discussion of the cortex, it's the input from the hippocampal system to a dendritic branch that guides receptive field expansions by influencing when synaptic weight increases can occur on the branch. So, cortical receptive field expansions are guided by outputs from the perirhinal and parahippocampal cortices. Perirhinal and parahippocampal receptive field expansions are guided by the entorhinal cortex. Entorhinal cortex expansions are guided by CA1, although, as I mentioned, there are a couple of extra structures between these two, the subicular complex, that we needn't discuss. CA1 receptive field changes are guided by CA3, and CA3 changes are guided by granule cells in the dentate gyrus. Let's have a closer look at that particular step. There are granule cells in the dentate gyrus and pyramidal neurons in CA3 that all have receptive fields within the same sources of information. So some granule cells will have somewhat similar receptive fields to some CA3 pyramidals. Then there are interneurons in CA3 that inhibit the pyramidals. Granule cells target pyramidals that have somewhat similar receptive fields. And note that this could be because the granule cells tend to target pyramidals that are often active at the same time. The direct excitatory outputs from a granule cell target branches on the CA3 pyramidals and encourage receptive field expansions in pyramidals with similar receptive fields. The indirect inhibitory outputs also target CA3 pyramidals with similar receptive fields. One pyramidal will be targeted by multiple granule cells on the basis of some degree of receptive field similarity. So, expansions of CA3 pyramidals are guided by inputs from the dentate gyrus. However, this begs the question of how dentate gyrus receptive fields are guided. Well, although hippocampal system inputs can guide synaptic weight increases, synaptic weight increases will occur if a branch fires, even without a hippocampal system input. And once a branch has been initiated, it can probably continue to evolve to some degree without guidance, even in the cortex. But in the dentate gyrus, receptive fields must be bootstrapped, more or less without guidance. So the dentate gyrus guides CA3, and CA3 guides CA1. Receptive fields in CA3 will therefore be more sharply focused on appropriate groups of cortical columns than the granule cells, and CA1 pyramidals that drive the changes will be even more sharply focused than CA3. And in fact, there's another factor that sharpens the CA1 fields even more. CA3 and the dentate gyrus get their inputs from layer 2 of the entorhinal cortex, but CA1 gets inputs from layer 3, and these inputs will correspond with somewhat more narrow groups of cortical receptive fields. But the granule cell receptive fields expand without guidance, which may be the reason that the dentate gyrus is almost the only structure in the brain in which new neurons are generated after birth. In other words, unguided expansions mean that receptive fields eventually become too general, and the brain discards them and creates new ones. Of course, the CA3 receptive fields preserve the receptive field information, so it isn't lost, and the CA3 fields could be used to bootstrap the new granule cells. In the cortex discussion earlier, we already discussed the guidance of receptive field expansions at the neuron level using extra inputs that guide branch condition changes, and how a branch that doesn't have enough total synaptic weight to contribute to the firing of its neuron can contribute with the aid of a hippocampal system input, and if the neuron fires, the back-propagating action potential increases the recently active synaptic weight so that the branch can fire in response to a future repetition of the same inputs without the aid of the hippocampal system input. So the same mechanism applies to receptive fields within the hippocampal system, and the deeper level descriptions in terms of chemistry are also more or less the same. However, there is another information mechanism that's relevant. Once a branch acquires enough total synaptic input weight to fire without the aid of the hippocampal system, it'll become less appropriate for the hippocampal input to contribute. So the weight of the hippocampal input needs to decrease over time. One available mechanism is the decrease in synaptic weight if an input arrives after the neuron's fired. So once the branch condition has become established, the branch detects its condition without the aid of the hippocampal system, so there could be a tendency for any hippocampal system inputs to arrive after the branch and neuron have already fired. And if the timing is correct, the weight of the hippocampal input will therefore tend to decrease over time. Now, I've left out some parts of the hippocampal system, like CA2, that's located physically between CA1 and CA3, and the subicular complex, which is located on the output route between CA1 and the entorhinal cortex. And I've also left out connectivity with the amygdala and also some subcortical structures like the thalamus, the hypothalamus, and the basal forebrain. All this connectivity makes up what I've been calling the hippocampal system, and I'll discuss the operation of this system as a whole after I've discussed the roles of the amygdala and the subcortical structures individually.